We have Dr. Scott Solomon joining us. So Dr. Solomon is an associate teaching professor in the Department of Biosciences at Rice University and the author of Future Humans Inside the Science of Our Continuing Evolution, published by the Yale University Press. So he is a writer slash producer slash scientific consultant for Becoming Martian, a Curiosity Stream show, and a professor with Wandrium slash the Great Courses and the Glasscock School of Continuing Studies. He's also a research collaborator at the Smithsonian Institute National Museum of Natural History and the host of educational travel adventures in wild places. So Dr. Stott.
Thank you very much for the invitation to participate in this conference. I think it's a very interesting topic, of course, and one of the things that I want to convey in my remarks today is how important I think it is that people from different disciplines come together to discuss the human future in space. I myself am an evolutionary biologist by training. I teach courses at Rice University in Houston, Texas, in ecology and evolutionary biology. And my research is on the ecology and evolution of ants. And for the last 12 years or so, I've become very interested in the possible evolution of humans in space if we are to establish long-term settlements beyond Earth. And so what I want to emphasize today is that I strongly believe that in order for us to be successful in establishing human settlements in space in the long term, we need to draw on research from a wide range of different disciplines. The emphasis on medicine here, I think, is very important. Obviously, safety is first and foremost priority for any human exploration and time and space. But of course, my background as an evolutionary biologist causes me to think very long term into the deep future. And that has caused me to draw on research from disciplines ranging from genetics to anthropology, sociology, psychology, microbiology, medicine, physiology, and others. And it's great anytime there's opportunities for people from different disciplines to come together and talk about what we know, what we don't know, where we would like to see the research moving forward. So what I want to do today is to talk about what to me seem like 5 of the most pressing questions that we really need to be addressing if our hope is to be able to successfully establish human settlements in space. So clearly, I probably don't have to convince this audience that the notion of human settlements in space is something interesting and important. I think we're all aware that efforts are underway to try to create human settlements in space. Some of those are human settlements that would be a short-term presence, a base on the moon, for example, that would have people going and spending some amount of time there, weeks, months, years, but ultimately returning to Earth. My talk will focus more on the possibility of long-term human settlements in space, settlements that would involve people spending their entire lives there and reproducing. And that's where I think we still have a long ways to go before we're ready to do that, but we need to be thinking about what steps should be taken in order to get there. So the first question I want to address is, how many people do we need for such a settlement? What is the population size that would be necessary for a long-term human settlement to be successful? And this is a question that, again, you can approach from many different disciplines. One way that I've tried to approach thinking about this question draws on my background as an evolutionary biologist, because in many ways, settling space is very reminiscent of the process that happens on Earth all the time when some type of species goes and colonizes a new habitat. That could be an island that pops up out of the sea, or it could be a patch of forest when a tree falls that becomes cleared and organisms are able to move in that weren't able to live in the intact forest before. Basically, anytime that there's a opportunity for individuals that weren't there to go and establish a new population, we get something that is similar to the process that we're thinking about in terms of settling a new place in space. And so we've learned quite a lot in evolutionary biology about the population size that is necessary for such a population to become established and successful. And what are the consequences of having a population size that's too small? So there's actually a phenomenon in evolutionary biology called the founder effect. And the founder effect is essentially the effect of having founding members of the population. It's the long-term effect on that population of the number and identity of those founders. And in essence, what the founder effect shows us is that the smaller the number of individuals, the less likely that population is to be successful, which is not a surprising conclusion. But it also tells us that when a population size that is founding a new settlement is small, that those individuals that establish that new population, they have a disproportionate effect on the identity, on the characteristics of the population that will become established later. So, one of the examples of this is how, whatever those individuals are, whatever traits they have, well, those are the traits that are likely to be, common in subsequent generations of that population. And it's unlikely that those individuals that we're talking about, a small number of individuals drawn from a larger population. It's unlikely that those small number of individuals are representative of the entire larger group that they came from. And because of that, the new population is likely to be different from the larger group from which they were drawn. And so the founder effect shows us that anytime a small number of individuals establishes a new settlement, that it is very likely that that new population will be different from the population from which it came. And the smaller that group is, the more likely they are to be different. But there's a second point to the founder effect, and that is that the smaller the number of founding individuals, the less genetic diversity there is going to be in the population, even if it is successful. So not only because there's a small number of individuals, but when you have small numbers of individuals, you get a phenomenon known as genetic drift, which is actually an evolutionary process by which the number of how common a particular trait is in a population fluctuates randomly. It could randomly become more common, or it could randomly become less common. And it's much more likely that it becomes randomly less common to the point that it disappears. When traits disappear, it reduces the genetic diversity of the population. So founder effects are tightly correlated with having low genetic diversity. And that leads me to my second key question. And that is, how should we be choosing the individuals that would establish a human settlement beyond Earth? And I think that we really will be forced to go back to the drawing board, so to speak, when it comes to how we select individuals for space travel, because so far, space organizations like NASA, ESA, and others, they primarily have chosen individuals who are very physically fit, very mentally fit, of course, very capable of doing work under stressful situations. They tend to be adults within a fairly narrow age range, who have had already a lot of experience in doing relevant types of challenging work. And that makes a lot of sense for the type of work that has taken place in space travel up until now. But if the goal is to establish human settlements, then I think we really will need to revisit those criteria. And specifically, it will become very important to try to create a very diverse group of settlers. And I mean diverse in many different forms. Diversity, of course, can mean many different things. And so I think what we need to clarify here is that the component of genetic diversity is going to be absolutely essential for the success of a future colony. Why? Because what evolutionary biology shows us is that populations that are more genetically diverse are more stable, and more resilient, meaning that they're more likely to be able to survive through challenging times and stressful conditions. Also, genetically diverse populations are better able to adapt to changing conditions. And as we'll see, that's going to be essential for long-term success of a human settlement beyond Earth. So we'll need to be thinking not only about people who are going to be able to, tolerate the trip and bring important skills to the work that needs to be done. Obviously, those will still be important as they are now, but we also need to think about the genetic diversity of those individuals. I think an argument could be made for, trying to intentionally select from all of the genetic diversity of the human species, which is something that, to date, we really have not done when it comes to astronaut selection, cosmonaut selection. So I think this is going to be a complete pivot when it comes to how participants are selected. Now, as I said, my focus here is on long-term human settlements. And if the goal is to create a self-sustaining human settlement, then by definition, we will be requiring human reproduction. And this brings us to one of the most fundamental questions, which is human reproduction beyond Earth possible? If it is possible, what are the effects of the conditions that people would be exposed to? And what are the challenges that would come with human reproduction? I'd like to break this down into three different, separate but related processes or steps. The first being fertilization. Is a fertilization of a human embryo possible? Are there consequences of the environment of space that could be problematic? The second being pregnancy, and the third being childbirth itself. And so this is where it's quite interesting that we have some research that has been done on this. There have been studies in low Earth orbit and simulated microgravity that have included organisms ranging from sea urchins to some species of fish, some amphibians like salamanders and frogs, some birds like chickens, as well as some rodents, mice and rats. And the conclusion from the weight of the evidence in these studies is that we really don't know what the outcome would be for human reproduction. It seems that each of these steps is possible, but there have been studies that have found some problems that have popped up for each of those steps. So from fertilization through implantation and pregnancy, very little on childbirth itself. And of course, we have to extrapolate from these animal models to a human system. So this is an area that I think if our goal is to create long-term human settlements beyond Earth, we really need to have much more research in space conditions in low Earth orbit or in simulated microgravity that can help us to understand what will be the challenges of each of these steps in human reproduction: fertilization, pregnancy, and childbirth. And a related question, but I think one that is worthwhile separating, is what happens after a child is born? How is child development affected by the conditions beyond Earth? So far, I haven't really specified where I'm talking about. When I say beyond Earth, this could be in low Earth orbit in a space station. This could be on the moon. This could be on Mars. This could be elsewhere. But of course, as we know, the conditions have some similarities in that the gravity environment is likely to be different from Earth gravity, likelihood of enhanced or increased radiation exposure, and other situations. So we can start to draw some parallels between the work that's been done, for example, on low Earth orbit to what the situation might be like on the surface of Mars. So I specifically highlight child development because we know what the effects are of low gravity on an adult human. We know that muscles begin to atrophy, that bone density decreases, and demineralization of the skeleton occurs. We know that can be counteracted to a certain extent through exercise and resistance exercises. But of course, these still remain challenges for people that spend even short amounts of time in low Earth orbit. So the big question to me is, what would be the outcome for a child, a growing human who needs to develop a skeleton that is going to be functional for the conditions, not only where that person is, but also if they are going to be traveling elsewhere, such as coming back to Earth. And so I think we need to better understand what the effects would be of microgravity on a growing child's body. Related to that is a question about the microbiome, something that I think we often don't think as much about when it comes to space travel and some of the challenges that we'll face. But we've learned quite a bit in the last decade or two about the importance of the microorganisms that live in and on the human body. In fact, we know now that we cannot live without these microorganisms. And yet we acquire these microorganisms from our environment after we are born. And many of them we get from the people around us, including from our mother through the birth process, as well as from parents, siblings, close playmates, et cetera. And much of that establishment of the microbiome happens very early in infancy and childhood. And it's almost certainly the case that moving beyond Earth would result in at the very least, a change in the types of microbes that we're exposed to that are able to inhabit the body and form the microbiome, and most certainly a reduction of diversity in the types of microorganisms. Interestingly, that reduction in diversity parallels what we have seen as human civilization has advanced. If we look back at the microbiomes of people living 10,000 or more years ago, we see they had a much greater diversity in their microbiomes than most people do living today. Some people have suggested that reduction in microbial diversity has could possibly explain the rise of certain, for example, autoimmune disorders and other conditions that have become more prevalent in recent years. We don't know if that's the case, but if we're going to be talking about a drastic reduction in the diversity of microbes that can possibly inhabit the human body in space, we need to have a much better understanding of what the consequences would be of doing that. And for the fifth and final question, we need to really understand more about how adaptation to conditions beyond Earth would affect the ability of people to be able to return to the Earth. I've already alluded to this in my comments about what might happen to the musculoskeletal system. It seems possible that if a child is born, for example, on Mars and is exposed to the 3/8 gravity of Mars, that their skeletal system would be weakened to the point where leaving Mars and returning to Earth and experiencing not only the re-entry to the Earth's atmosphere, but also the 1G environment here on Earth might simply be too much for that person's body to be able to tolerate. Going back to the notion of the microbiome and the importance of the microbiome, I think we have to think about this in the same context, because it's possible that by not being exposed to the diversity of microorganisms that we normally are here on Earth, and almost certainly not being exposed to many of the same types of pathogens, infectious disease agents as we are here on Earth, that the immune system of people living beyond Earth could be compromised or weakened, or perhaps over generations even atrophy, to the point where returning to Earth could be extremely dangerous, if only because the people would not be able to tolerate the types of even common microorganisms that we have here on Earth, and something like the common cold could end up being a lethal threat. So I also want to make a distinction here between the difference between acclimatization and adaptation. So what I mean by adaptation here is really the way we use it in evolutionary biology, which is change over multiple generations. And so in that sense, with each new generation, we would expect that the individuals living beyond Earth would become better and better adapted to the local conditions, the conditions, for example, on Mars, which would make them better at surviving and thriving in that environment. But with each passing generation could make them less and less fit for returning to the planet Earth. And this is something we have to really take seriously, because we need to think about what would be the consequences of creating a situation where people multiple generations from now are unable to come back and experience everything here that we love about planet Earth and their entire heritage. So I think I'll stop there. I want to thank the organizers once again for inviting me to present today, and thank everybody for your time and attention. And I look forward to an interesting discussion ahead. Thank you very much.